Okay, minasan, konnichiwa, Zamurai Engineer desu. So let us discuss one-way slab in this segment of live stream. So let us first check the sound. If we are receiving the sound clear enough. Anybody? Anybody would like to confirm clarity of the sound? Okay, so shout out, Charlize. Therefore, we have to proceed on our discussion. One-way slab. So, reinforced concrete slabs are large flat plates that are supported by reinforced concrete beams. So, the slab is used for flooring. Okay? It could be supported by columns directly or by walls, by structural walls. Okay? And if they are supported on two opposite sides only, they are referred to as one-way slab. So, on two sides, if they are supported on two sides, okay, that is what we call one-way slab. Okay? So, a slab could be supported by the ground if that is flooring on the ground floor. Okay? So, one-way slab is assumed to be a rectangular beam. Okay? So, it is also a rectangular beam. So, what we did in our design method up to this point can be used to design the one-way slab. So only that normally a beam will tend to expand laterally somewhat as it bends, but this tendency is to expand by each of the 12-inch strip is resisted by adjacent 12-inch. So we can design a slab by cutting off, okay, 12-inch one-way slab design per 12-inch. In reality, the slab is very long, but we can cut a strip. Theoretically, hypothetically, we are designing only this strip, and that is useful because per 12-inch, 12-inch is equal to 1 foot. So if you are using SI unit, we are going to design it by 1 meter. So per meter rather than per foot. Okay? So that is how we do it. The design of slab. Okay? So the thickness for a particular one-way slab depends on the bending, deflection, and shear requirement. So we have the computation for that, for deflection particularly. Okay, because of quantities involved in the floor slab, the depths are rounded up to closer values than are used for beam depth. So, in SI unit, every 5 mm, we are rounding up in 5 mm rather than whole number, 5 mm, because this is a slab. That is the only difference between beam and slab. Okay? So if you are using English units, rounded up to the nearest 1/4 inch. Okay, 1/4 inch rather than 5. So 1/4 inch is about 6.7. That is about 6.7 mm. So in SI unit, we are rounding it up to 5 mm. Because of what? For easy measurement. You can easily measure 1/4 inch rather than 0.3 inch. It's very hard to measure the actual slab measurement. 0.3 in real construction. Okay? So, the same is true with 5 mm. That's why we are rounding up to the value nearest 5 mm. For example, 113, we will round it up to 115. Right? Or 112, we will round it up to 110. Okay? So, that's how we do it. Okay? So, for SI units, the minimum percentage of reinforcing are 0.002 for grade 300 and grade 350 steel. And use 0.0018 for grade 420. So, these have to be memorized. You have to memorize this. 0.002 is the value of raw for grades 300 and 350 and 0.0018 for grade 420. Okay? You have to memorize this. In English units, okay? Okay. What is in English units? We have to use this. 0.002 again. Okay. For grade 40 or 50. Okay. And then what else? For grade 60, 0.0018. So, obviously, similar to this. Okay? Similar to SI unit. Okay? The reinforcing may not be spaced further apart than 5 times the slab thickness. So, if the slab thickness is 100, so 5 times, the spacing is 500. So, 100 times 500 mm. So, that is spacing. Reinforcing, spacing of reinforcement. Okay? So, remember that. Remember this. Okay? So, this one. 0.0018 if we are given grade 60. The same here. Okay? 0.0018 for grade 420. So, the equivalent of grade 60 is actually 414 or 415, not 420. But, again, the conversion is actually 420 still. Okay? So, what are the other conditions in designing this? Okay? So, should structural walls or large column provide the principal resistance to shrinkage, temperature movement, it may be very necessary to increase the minimum amounts listed. Okay? So, it depends. Shrinkage and temperature steel serves as matte steel in that it is tied perpendicular to the main flexural reinforcements. Okay? And holds it firmly in place as a mat. This steel also helps to, that's why if you are placing the steel bars to form the mat for the slab, actually that is the right way to call it, the mat. Okay? Matting for slab. Okay? Reinforcement. Okay? So that is what they call it in construction. In similar manner, the AASTO, recall, this is for highway, road networks, and highway design. Okay? Same. Gives minimum permissible amounts of reinforcing in slab transverse to the main flexural reinforcing for lateral distribution of wheel loads. Okay? So, similar manner. So, slab is similar with the design of roads. However, the difference that the loading is too much heavier in roads rather than in building. The loads are heavier in live load and different from the building. Okay? So areas of steel are often determined for 1 foot width of reinforcement concrete slab. So per 1 feet, no? 1 foot by 1 foot. Every design of slab, 1 foot. So one way slab, 1 foot, 1 foot, 1 foot. Okay? For a 1 foot width of concrete, the total steel area obviously equals the total or average number of bars in a 1 foot width times the cross-sectional area of 1 bar. This can be expressed as 12 inches per bar, spacing center to center. Okay. So we have this following example. Okay. So number 9 bars, 6 inch on center. Total area in 1 foot width is equal to 12 over 6 times 1, that is 2 square inch. Okay. We are dealing with 6 inch spacing. Okay. So if you are dealing with the same size, 5 inch on center, so rather than 6, so 12 over 5, the steel area is 2.4 rather than 2. Okay, so these are the conditions on designing slab. So example, design a one-way slab for the inside of a building using a span, loads, and other data given in figure 4.8. Normal weight aggregate concrete is specified with a density of 145 pounds per cubic foot. The usual value is 150, but here it is specifically said the given is 145, not 150. Okay. So where is the figure? This is the figure. Okay. So live load 200, FC prime 4,000, FY 60, span length 10 feet. Okay. So let us design the one-way slab. So first, minimum total slab thickness H. Okay. If deflection are not computed, we can actually see the table 4.1. So in the table 4.1, we already memorized the table. Okay, cantilever 1 over 8. Okay, for beam. So for simple support times 2, 1 over 16. And then plus 2.5, 1 over 18.5. Then again plus 2.5, 1 over 21. But for one-way slab, 1 over 10. For cantilever, for simple beam, that is 1 over 20. For one end fixed, that is plus 4, 1 over 24. And for two ends fixed, that is 1 over 28. Very easy to memorize that table. Okay? So here, so we are given simple support, so that is 1 over 20. So 10 feet divided by 20 times the conversion factor, so therefore we have 6 inches. So H must be 6 inches. So 6 inches is 1 foot. Okay. 1/2 feet. 6 inches is 1/2 feet, and that is actually 150 mm. 150 mm. So if that is your H, D is approximately less than that. So we have the cover. How much the cover? 3/4 inch. Okay. So cover minus 1/4 inch for estimated half diameter bar of size. So therefore, so 6 inch minus 3/4 minus 1/4. Okay. So 1/4 is the estimated half diameter of bar size. Okay. So that is half diameter. So 3/4 is the concrete cover. So therefore, if you subtract 6 minus 3/4 minus 1/4, that is equal to 5 inch. Okay. So our D is equal to 5 inch. So the moment is calculated using D. Okay. And then the amount of steel required is determined. If this value seems unreasonable, a different thickness is tried. So that's how we design slab. Okay. So we are designing what? 12-inch wide type of beam. We are designing a beam with 12-inch width. Okay. So therefore, the same dead load of slab 6-inch. Okay. Conversion factor 150. Okay. He did not follow the correct given. I just told you. The given is 145, not 150. So this is wrong. Okay. So the solution is wrong. Okay. Take a look. Do you notice? I could easily see where is the wrong. What more if you are a student solving a problem? I can even find out the wrong of the solution of expert. These are expert. I am not better than this expert, but I can find out where are the wrong solution. Okay? I can find out where the wrong solution. So the given is 145, but he used 150. Okay? So I could easily find that out. Okay? So don't ever imagine that your solution will be able to pass without me looking at your solution and finding out any problems with your solution. That's why you really need to try to understand and try your very hard to design, okay? Using the knowledge of this document, of this code. Okay? I can find out where are your mistakes. Okay? I am not an expert like this author, but I can find out the mistake. Okay? Okay? I can find out the mistake. Wrong solution. Okay? So let us just give him a benefit of the doubt. For example, this is 150. I just said that the normal value is 150. Okay? So use the 150. So these are the dead load and live load. Therefore, we can solve for the WU. Okay? Meaning, what do you mean by WU? Uniform load. Okay? 1.2 dead load, 1.6 live load. So therefore, 410. So let us compute MU. This equation is for simple support. Therefore, we have this one. So this is different if you are given cantilever. If you are given fixed end, this is different. Okay. So we can determine Rn. So this is Rn is equal to mu over phi bd squared. So that is substitute the values. Okay. Okay. That's correct. Rho. Therefore, from the table, using this value of Rn, tabulated value, or you can use the formula. So this is the value. Therefore, it is greater than the minimum. It is okay. So therefore, we can find out the still area, rho BD. Rho is this one, B, and D. D is 5 inches. Okay. So 12 inch is the constant strip. Okay. The wide slab is broken down into several pieces of 12 inches. 12 inches strip. Okay. Okay, therefore we have what? 0.236. Okay. And use that value. Okay. So to find out the size of the bar. So number 4. Okay. So number 4. 10 inch from the table. So that is 0.24, very near the value 0.236. Okay. The spacing must be less than maximum of 18 inches as per ACI. Okay? 18 inches. 18 inches is what? 450. In SI unit, I know it to be equal to 450 mm. So 18 inches. Okay? So the maximum spacing must be less than that. So in real application, in construction, you are going to measure if they are rolling the slab steel bars, so you can measure that spacing must be less than 450. Okay, that is the code provision. So number 4 bars are placed below number 3 bars in this case. Okay. The number 4 bars are primarily flexural reinforcing, and the value of this is based on this assumption. The number 3 bars are for temperature. So number 3 bars are smaller than number 4, and number 3 bars are for temperature and shrinkage control. Okay. Okay, so therefore we have the explanation. The designers of reinforced concrete structures must be very careful to comply with the building code requirements for fire resistance. Okay? If the applicable code requires a certain fire resistance rating for floor system, that requirement may very well cause the designer to use thicker slab than might otherwise be required to meet the... So, you have to check it. So, your solution with the design of your slab must be checked with the requirement for fire resistance. Right? In other words, the designer of a building should study carefully the fire resistance provisions of the governing building code before proceeding with the design. Okay? So, this is very important. Okay? So, I would like to screenshot this one so that we can review it later on. Let me have 30 seconds to screenshot. Okay? I am taking screenshot of this important concept. So, fire protection. Okay, so fire protection. Because I am very much interested in fire protection. Okay. So, I am just telling it to you, but I will give you the easier design problems that you do not need to do this checking in our exam or quiz. So this is for actual professional construction work. Okay? So that is not for you. I am just telling you so that you are aware. You must be aware of this. Okay? But I will not give you the burden of designing against the fire code. Okay? So next, very important and for our discussion of slab. This is very important for the discussion. Notice that we are designing slab simple support. Now we are dealing with cantilever and continuous. So continuous in one end, continuous on both ends. Cantilever, right? So obviously, the value of estimated H is equal to 1 over 10 and 1 over 8, right? So if 1 over 8, that is for RIPbE type of slab. So 1 over 10, that is for one-way slab, okay? So for continuous, we have either one end or both ends. Okay, so up to this point, only statically determinate members have been considered. The very common situation, however, is for the beams in slab to be continuous over several support. Beams in slab in reality are somewhat continuous. There are more applications with continuous beam in slab, particularly in building. So in bridge, more application is simple beam. Okay, simple beam, simple support. Okay, but in buildings, more application is on continuous and cantilever. Okay, so therefore, as shown in the figure, so this is the figure. So we have what? Cantilever beam here. Okay, so we need to know about these things, and this one is the continuous slab and beam, and as you can see, we have what? The moment diagram. These are the moment diagram. Okay, so placement of bar. How to place the bar in continuous beam. So this is the tension bar, then stop it there, then bottom bars here. This is also a tension bar. Here, this is also a tension bar, but this is now top bars, bottom bars, top bars, bottom bars, top bars. They are all tension bars because this is a continuous beam. Okay, between the span, in the middle of the span, those are tension, tension, tension. But in the support itself, the support here is the support. In the support, the tension side is on top. Okay, take note. If we are talking at the support, the tension side is on top. Okay? If we are talking in the middle of the span, the tension is at the bottom. Okay? So, all of these are tension steel bars. Okay? That's why we are saying that this is positive steel bars, negative steel bars, but they are not A prime S. They are not A prime. They are only A S. Only AS, not A prime. Negative AS, positive AS. Okay? Are we clear? Oh, this is how we design for continuous and cantilever. Okay? So when we are dealing with what? So all of the theories, concept, principles learned from theory of structures. When you are dealing with fixed support or continuous beam, you have to use that. There are three types of indeterminate beam in your study of theory of structure, and there are also three types of determinate beams. So all of those must be reviewed. I will not discuss it here, but in problem solving, you have to use those formulas. Okay? In exam, in quiz, you have to use those formulas. SI example. Okay, we have the requirement: design a rectangular beam for a 10-meter simple span to support a dead load of 20 kilonewton per meter, not including the beam weight. So we will proceed to estimate the beam weight. Okay, live load 30 kilonewton per meter. Use rho is equal to 0.5. Rho balance 0.5 rho balance this time. So it is 0.375 to 0.75. So that is the range you can select your own Poisson. Okay. So FC prime is equal to 28 megapascal. And Fy is equal to 420 megapascal. And concrete weight is 23.5. Okay, so in the code, this is 23.6 in the code. Do you not use the ACI thickness limitation? Okay. So therefore, solution, using this given, assume that the beam weight is 10 kilonewton and phi is equal to 0.9. These are two assumptions. Okay, let us find out. So uniform load, so 1.2 30 plus 1.6 30. Okay, what can you say about this? So we use the beam weight, self weight, because the dead load is only 20, so plus 10, so it is 30. So therefore we have 84. So for what type of beam? Simple span, so simple beam. Okay, it is not a continuous, it is not a cantilever, so simple span formula. So W L squared over 8, so 1050 kilonewton meter. So find out the rho. This is 0.5 times the rho balance. Okay, so rho balance is 0.0283 from the table. So therefore we can find out this value. So therefore the design strength is equal to phi rho FYBD squared, quantity 1 minus 1 over 1.7 rho Fy over Fc prime. Take note, this equation is for SI unit. Okay, so using that, we can have this value. Okay, and only the BD squared are the unknowns. So solving for BD squared, so we have 2.2432 times 10 to the 8th power millimeter cube. So let us have 3 alternatives. You have to try 3 alternatives and choose the best one. So we can choose 500 by 670. Okay, so let us check if that is okay. So 500 by 800. So therefore 800 included the concrete cover, therefore T is 680. So beam weight, is from this dimension we have 9.4, and our assumption is 10. So it is about okay because it is very near. Okay, our assumption is 10. It is about 10 because the answer is 9.4. Okay, so it is okay. So we can therefore determine the steel area by using this value, and therefore this area is okay. So from this area we can find out from the table or from actual computation the size of the bars. We use 6 pieces of number 32 bars. We can have this total. Okay, so the total is actually 4,914. Our requirement is 4,800. So in my case, again, this author uses greater than this. I am using less than that. A little bit less than this. I am using because I want the design to be ductile. I want the design ductile. This author also wants the design to be ductile, but he is using greater than. I am using less than. Okay. So therefore, find out the value of A. So the same formula here. We are always using 173 is the result. So the difference between C and A. So 0.85. Why? Because the FC prime is about 300. What is the FC prime? FC prime is 28. 28 is equal to 4,000. So actually, 27.8 is the value of 4,000. So this is 4,000 KSI or 4,000 PSI. So 4,000 PSI, that is beta 1 is equal to 0.85. So here it's correct. No? 0.85 beta 1. So therefore, the value of C is 204. So tensile strain, you can find out to be 0.0070. And that is greater than 0.005. Therefore, this is okay. This is ductile, tension controlled. So therefore, phi is equal to 0.9 is okay. We prove it. We are able to prove it that this is okay. Okay? So, following that, therefore, we can find out the minimum value of width using the table or using your estimate computation. So, that is 267. So, that is less than our actual width, which is 500. So, therefore, that is okay. So, this is for spacing of the bars. This is just for, this one is only for spacing of the bars. So, since it is 500, so the steel bars will be good in spacing inside the 500 mm. Okay. So, again, for our use of the tables and appendix, we can find out the Rn to be equal to 5,200 by interpolation. Okay, so using this, we can find out. So Rn cross multiply to determine BD squared. So using the Rn, so our answer is 2.2432, which is also very near. Okay, I think that is very near in our answer here, 2.2432. Okay, that is very near. So therefore, using different alternative method, we have the same answer. So since we have the same answer, we will not continue. So we will not continue. It will give us the same answer. So this one will give us the same answer. Okay, different method. Okay, so therefore, you can have this type of arrangement using 6 pieces of number 32 bars. Okay. Okay, any questions? Any question? So, not only the dimension of 500 by 800, the location of the reinforcement bars must be included in your answer. The location meaning 80 mm, then another 80 mm on the other side. So at the middle we have these bars. So 80 mm concrete cover, so another 80 mm second layer. Okay, so that is how you have to label your answer. If not, your answer would be incomplete. Okay, incomplete information meaning construction worker cannot construct your building if you have incomplete information. For example, here, if there are no values for 80 mm here, so 80 mm here, 80 mm here, if there are no such values, the construction workers cannot do this beam. Okay, without that specific information. That's why you need to do it. So we have a computer example that we will get a special time for this. So therefore, we are through with all of these chapters. Okay? So just remember to practice problem solving on your own. use your own sketch of your house using the engineering plan. So there are plenty of problem solving opportunities for yourself. Any question? Any question? So if there are no questions, just use our GC. If you have question later on, by the way, we have to end our discussion right now. I will just post instruction on our GC. Again, this is your professor, Dr. AP, preaching engineering for nation.